Good afternoon to all. We have already seen some production schemes for this generator. Let us discuss few more production schemes for this generator. Okay. So let us discuss about this balanced earth fault protection of the generator. So, so whenever we want to protect a small size alternator or generator, in what the engineers have seen it that the neutral point, this is the neutral point, isn't it? This is the neutral point, this is the generator winding, three-phase winding. This is the neutral point. So the neutral point of the three-phase winding will be often connected internal to this single terminal. Okay. So the neutral point of this three-phase winding is often connected internal to the single terminal. So it becomes difficult to use merge price circulating current protection for small size generators. Why? Because if you observe here, this is generator winding, three-phase winding, and you can see here the neutral point is far away from this winding. When it is a big size generator, when the size of the generator is enough large, there will be sufficient space for the cities to be connected across the towards the neutral side as well as on the other side of the winding. Whereas whenever we are using whenever we are using a small size generator, then the neutral ends of the three-phase windings are often connected internal to a single terminal. Okay, therefore it is not possible to use the merge price circulating current protection. Okay, so because there is no possibility for accommodating the necessary current transformers. You have just now have shown you the image. Okay, so we have to accommodate the current transformers here. Okay, on each phase. Okay, on the neutral connection side. Okay, so but here if you see in this image, there is no space at all. Okay, there is no sufficient space to place the CTs. Okay, that's why merge price protection cannot be used for small size alternators protection. Okay, so it is better to go for some other protection for protecting the small size alternators. That alternate protection method is balanced earth fault protection. Okay, so some other method instead of going for merge price circulating current protection, we can go for another method, that is balanced earth fault protection method. Okay. So there is a means this protection can be only used for protecting the alternator from earth faults, but it cannot be used for protection against the face-to-face faults. Okay, unless these earth faults, unless these face-to-face faults develop into earth faults. Okay, so this balanced earth fault protection scheme can provide protection to the alternator windings only during earth fault condition if LG fault occurs. Okay, so if face-to-face fault occurs, this balanced earth fault protection scheme cannot provide protection against face-to-face faults. But okay, if these face-to-face faults okay develop into earth faults, then they can be means those faults can be removed or those faults can be interrupted by this balanced earth fault protection scheme. Okay, so you can see here in this image, you can see on the other side of this alternator windings, on each phase, CTs, primaries of the CTs are connected and their secondaries are connected in parallel. Okay, so RYB phase. Okay, so primaries of the CTs are connected in series to the one end of this alternator windings, and their secondaries of the CTs are connected in parallel. And similarly, okay, there is a single CT, okay, current transformer on the conductor which is joining the star point of these three generator windings, okay, alternator windings to the earth. Okay, So there is a single CT which is connected to the star point and between the earth, between the star point of neutral point. Star point is nothing but neutral point. Neutral point of this generator winding on the earth, there is a single CT, and the secondary of this CT is connected across means connected to the secondaries of these three cities by some pilot wires. Okay, so this the zone between these three cities and this single city is the protected zone. Okay, it is the protected zone. So across the secondaries of this city and these three cities, there is a relay connected here, and to the of course the moving contact of this relay, and the fixed contacts are shown here. You can see here. Okay, relay and the trip circuit is shown here. Okay. So this protected zone is only for protection of this alternator winding against the earth faults, not for face-to-face faults. So under normal operating condition of this balanced earth fault protection scheme, okay, the currents flowing through the primaries of these CTs, okay, because of the current flow in the primaries, definitely the EMS will be induced across the secondaries, and hence current will flow through the secondaries of all these three CTs. Okay, so the algebraic sum of the currents of all these three CTs, okay, so of course they are since they are connected in parallel, the resultant current that is coming out from this pilot wire will be equal and opposite to the secondary current that is flowing through this pilot wire. Okay, so the differential current that is flowing through the relay will be zero when the current across the current in the secondary of this CT1 is equal and opposite to the algebraic sum of the secondaries of these all these three CTs. Okay, all this CT2 of all these three phases. Okay, so this if this is I1 will be equal to IR plus IY plus IB. When I1 is equal to IR plus IY plus IB, equal and opposite, so the resultant or the differential current will be equal to 0. Okay, so no current will flow through the relay and the relay will not operate. Okay, so we can say that the current in this neutral wire is 0, and the secondaries of the neutral current transformer supplies no current to the relay. That is under normal operating condition. Now let us assume that fault has occurred. Okay, so I have considered two cases here. I have assumed that fault has occurred within the protected zone and outside the protected zone, and I have assumed the fault which has occurred outside the protected zone as F2, and I have assumed the fault which has occurred within the protected zone as F1. Okay, now if earth fault, LG fault occurs at F2, that is outside the protected zone, then the currents which are induced across the secondaries of the CTs as well as this CT which is in the neutral zone or the neutral wire which is connected to the neutral wire, the algebraic sum of these two currents will be equal and opposite. Therefore, the resultant current that flows through the relay is 0. No current will flow through this relay and hence the relay will not operate. So, if earth fault occurs beyond the protected zone, this relay will not operate. Okay, because it is not going to affect the operation or it is not going to disturb the current that is flowing in the primaries of these cities. Okay, so no current will flow through this relay, hence the trip circuit will not operate or trip circuit is not closed and circuit breaker will not open. Okay, now if earth fault occurs within the protected zone, okay, let us assume at F1. Okay, F1 is the earth fault, LG fault which has occurred within the protected zone. Okay, so the currents will no longer be equal. Okay, the algebraic sum of all the secondary currents of all these phase CTs as well as this current will no longer be equal. So the differential current will flow through this relay. The difference of this I1 and I1 minus IR plus IY plus IB is equal to whatever IR you will get or I2 you will get. Okay, that I2 current will flow through this relay. Okay, the difference of this algebraic sum of all the secondary currents plus this current. Okay, the difference of those two currents will flow through this relay, and when if that current exceeds the preset value of this relay, the relay will be energized and the trip circuit is closed and circuit breaker is open. Okay, so this is the operation of balanced earth fault protection. Okay, so if earth fault occurs, this is how the protection is provided to the alternator. Now let us discuss one more protection method or protection scheme for the alternators, that is stator interturn protection. Okay. So we have already seen the merge price circulating current protection scheme. In that, we have already discussed that circulating merge price protection scheme can be used for protecting the generator windings or alternator windings against the face-to-face and face-to-earth faults. Okay, but it is observed that this merge price protection cannot protect the alternator against interturn faults. Okay, in the same phase winding of the stator. Okay, so if you observe carefully, I am showing you some image here. In this image, if you see RYB, so RYB are the phases here. Okay, so till now, whenever I said RYB, you might have seen only one turn coil. Okay, okay, so you might have seen only one coil here in each phase. But if you observe here, you can see two coils here. So means the coil has been duplicated into two coils. One coil has been divided into two coils here. Okay. So in merge price protection, it is able to protect against the face to earth and face to face faults, but not against interturn faults. Why? Because current through this type of faults produce flow in the local circuit between the turns involved and does not create any difference between the currents entering and leaving the winding at its two ends where current transformers are applied. Okay, so I will show you the merge price protection. Okay, this is our merge price protection. So here what we have seen is that the current entering this is our one phase winding, okay, R phase winding. The current entering this winding and current leaving this, entering or leaving the winding should be same. Okay, current entering into the winding and current leaving this winding should be same. That's what is measured by the CTs of this phase R. Okay, so current entering and leaving, if they are not same, then then the differential current will flow through this relay and this relay will operate. Okay, that's what we have discussed. Okay, so now if the current entering and leaving are same, and if more number of turns are there in this winding, okay, the algebraic sum of current will leave this winding. Even though there is a fault, you may not be able to identify that by my merge price protection, since there is only we are measuring only the current entering and leaving. Okay, whereas if more number of turns are there, okay, if more number of turns are there in this one phase, you can see the whole winding has been divided into two windings here. Okay, so the current entering from here and current leaving from here is measured by these two CTs, but inside the current division, okay, current is dividing into two sections here. Okay, current is dividing into two sections. Okay, so if any fault occurs here within these turns, okay, that fault must be sensed by the relays. Okay, relay must sense that fault also. But in merge price protection, the CTs are provided at both ends of the windings, which just measures the entering current into the phase and leaving current from that phase winding. That's all. So this is a whole R phase winding. Okay, this is a whole R phase winding. Okay, so that the whole current is measured by these CTs. But within this winding, if more number of turns are there and if fault occurs within those turns, we need some protection. Okay. So, but it is in practice what the engineers think is that it is unnecessary to provide protection for interturn faults. Why? Because they invariably develop into earth faults. Okay, even if interturn fault occurs, they will develop into earth faults. If earth fault has occurred within a winding, then definitely we will go for merge price protection. Okay, that's why engineers think that there is no need to provide any protection for interturn faults. But protection must be provided if the cost of the equipment is very high. If it is a very small equipment and if more number of turns are not there, of course interturn fault is not required if there is only one turn. Okay, so for one turn generators like this, for one turn generators, interturn fault is not at all required. But some generators, such as hydroelectric generators, will have multiple turns. Okay. Okay, so this winding is a double winding. Okay, in each phase there is double winding. For R phase double winding is there, for Y phase double winding is there, for B phase also double winding is there in each phase. Okay, so if more than one winding is there in each phase, then interturn fault protection is required. Okay, so why double windings are used in hydroelectric generators? The reason behind is that they have to carry very heavy currents. Whenever the windings of the generator have to carry very high currents, then in such case we will go for double winding, triple winding, and so on. Okay, so we need to provide interturn protection. Okay, so what I am showing here is the schematic arrangement of the circulating currents and interturn protection for the three-phase double wound generator. Okay, so you can see here RC and you can see here R1. Okay, you can see R1 and RC. So RC is providing the merge price protection. Okay, I hope you are able to follow me. This is okay. So let us assume this is a single winding. If this is a single winding of phase R, on the both ends of this winding, we are providing CTs. Okay, so this is a single winding on both ends. Okay, this is a single winding. This is a single winding on both ends. I am providing CTs here. Okay, so that is our merge price protection. So okay, so these CTs are for merge price protection. These relays will sense whenever LG or LL fault occurs. Okay, in the windings. Okay, now this R1, R2, R3 are for stator interturn fault protection. Okay, these are the relays. R1 and RC both are relays. Okay, RC relays are for protecting the windings against face-to-face and face-to-earth faults. R1 relays are for protecting the windings against the interturn faults. Okay, and if you observe, the whole winding is divided into two windings here for in each phase. In each phase, the whole winding is divided into two windings, S1 and S2, and to each winding, primaries of CTs are provided. Okay, and their secondaries are forming a closed loop. Okay, the secondaries of these CTs are forming a closed loop. The secondary terminals of these two CTs are given to a relay R1. Similarly for each phase. Okay, so under normal operating condition, the current in the stator windings, okay, in each phase S1 and S2 are equal. Okay, so the currents in the primaries of these CTs, this is a CT, this is a CT. The current in the primaries of these CTs will be equal. Hence, the EMFs induced across the secondaries of these two CTs will be equal. Hence, current flowing through this loop will in the secondaries of the CTs will be equal. So since the currents are equal and opposite, of course, therefore no current will flow through this relay R1 and the relay R1 will not operate. Okay. So now if fault occurs, okay, it may be a short circuit between these two windings, S1 and S2. If short circuit occurs in between S1 and S2, okay, the current measured by the primaries of CT1, this CT and this CT will no longer be equal. Therefore, the currents induced in the secondaries will no longer be equal. So, therefore, the differential current will flow through this R1. When differential current flows through this R1, if it reaches the preset value of this relay, then the relay will be energized, hence the trip circuit is closed and hence the circuit breaker will open. Okay. So this is about stator interturn fault protection. Now let us discuss one more type of protection, that is rotor earth fault protection of the generator. So the rotor of the generator is normally unearthed, isn't it? Okay, stator will be earthed, but the rotor is unearthed. That is, it remains isolated from the earth. Therefore, if insulation breakdown occurs in the rotor, then it will not lead to any fault current. Means there will not be any leakage of fault current from this rotor to the earth. Okay, why? Because it is isolated from the earth. Rotor is isolated from the earth. Even if insulation breakdown occurs in the rotor windings, okay, there will not be any leakage of current. Okay, if single fault occurs. Okay, well, if once fault occurs due to insulation breakdown, okay, then there will not be any fault current to the earth. Okay, so the single fault, if it occurs due to insulation breakdown of the rotor windings, then it will not affect the rotor. But if this fault occurs and continues, okay, if fault occurs in the rotor due to the insulation breakdown, and if it continues for longer period of time, then it will damage the field winding of the generator. Okay, so it will damage the field winding of the generator. So for large generators, rotor earth fault protection system is used for protecting the field windings. Okay. So when one earth fault occurs in the rotor, then it is not necessary that the system is completely tripped. Only the relay indicates the fault has occurred, so that generator should be taken out of service at leisure. Okay, so if the fault occurs in the rotor, if it is a large machine, and if fault occurs in the rotor, and if it persists for longer duration of time, then the circuit breaker will trip, and since we are providing the earth fault protection here, the circuit breaker will trip, and the generator is to be taken out for service. So there are two methods of rotor earth fault protection. So one method is by using high resistance, and another method is by ACDC injection. Okay, so one method of rotor earth fault protection is rotor earth fault protection by using high resistance. Another is ACDC injection method for rotor earth fault protection. So let us discuss these two protections one by one. So first one is rotor earth fault protection by using high resistance. In this method, a high resistance is connected across the field winding of the generator. Okay, so across the field winding of the generator, a high resistance is connected. The midpoint of this resistance is grounded through a sensitive relay. Okay, the midpoint of this resistance is grounded through a sensitive relay, sensitive earth fault relay here you can see. So when fault occurs, this relay will detect the fault and send a tripping command to the circuit breaker. Okay, so the major advantage of this type of system is that it can detect the fault for most of the rotor circuit except rotor center point. Okay, except at rotor center point, at most of the rotor circuit it can detect the earth fault. Okay, so in order to overcome this, we must shift this tapping point. Here it is center tapped, that's what I have showed you, told you. Okay, so if we shift the tapping on the resistor from the center to anywhere somewhere else, then the relay can detect the midpoint fault of the rotor. So this is one method of protecting the rotor against the earth faults. Another method is ACDC injection method for rotor earth fault protection. So in this method, either you can inject AC or DC current into the field winding of the rotor and ground along with the sensitive over voltage relay. You can see here sensitive over voltage relay. This rotor is grounded with the help of a sensitive over voltage relay here and a current limiting capacitor. Okay, current limiting capacitor is there. This is it. Current limiting capacitor in case of AC. If I am giving AC supply, okay, here you can see auxiliary AC supply, AC or DC. If I'm giving AC supply, I will connect capacitor, current limiting capacitor. If I'm using DC, I will connect a current limiting reactor. Okay, so that's why I mentioned here in dotted form. Okay. Okay, so a single earth fault in the rotor will complete the circuit. Okay, if single earth fault occurs in the rotor because it is grounded here, okay, with the help of a DC source and the help of a relay. So if single earth fault in the rotor occurs, then it will complete the circuit, compresses the alternating current source, okay, AC source, okay, sensitive relay, earth fault relay, okay, and the earth fault that has occurred in the rotor will complete the whole circuit. Okay, and this earth fault will be sensed by this relay, and the relay will disconnect the healthy section from the unhealthy section. So major disadvantage of this system is the leakage of current flowing through this capacitor. Okay, there will be leakage of current through the capacitor whenever I'm using the source, AC source. Okay, the current will unbalance the magnetic field and increase the stress in the magnetic bearings of this rotor. Okay, so there is another disadvantage of using the AC supply is that relay cannot pick up the current that normally flows through the capacitance to the ground. Okay, so the relay won't be able to pick up the current that is flowing from capacitor to the ground. Okay, and if I'm using AC supply, much more care should be taken to avoid resonance between the capacitance and the relay inductance. This capacitance and relay inductance. Okay, so resonance should be avoided. Okay, so in order to overcome all these drawbacks, instead of using AC supply, you can use DC supply here. Okay, so instead of injecting AC supply, I can say I can inject DC supply. Okay, and this method of protecting the rotor against the earth faults by injecting DC supply is more simple, and there is no problem of leakage currents. Okay, so here when I am giving DC supply, one terminal of this sensitive relay is connected to this exciter. This is the exciter. Okay, and the other terminal is connected to the negative terminal of this DC source, negative terminal, and the positive terminal of this DC source is grounded. Okay, so when our fault occurs, that is earth fault occurs, fault current will complete the circuit path and fault is sensed by this relay, and relay will give a signal to the circuit breaker and circuit breaker will open. So this is rotor earth fault protection method by injecting AC or DC into the circuit. So one more method of generator protection is loss of excitation method or field failure method. Okay. So now, if the generator that I'm using or the alternator that I'm using is a large size machine, okay, then the large size machines cannot be allowed to run asynchronously for a longer period of time. Okay, with a relative motion between the stator field and the rotor will reduce large current in the rotor body, and therefore there is higher rate of heating of the rotor surface. Okay, so if the machine is running for is allowed to run asynchronously for longer period of time, then it is observed that the rotor surface gets heated up and loss of excitation scheme can be used to trip the circuit during that condition. Okay, so to protect the generator from loss of excitation, we usually use a DC offset connected to a Moog relay. Okay, you can see here Moog relay. Okay, so a DC offset is connected to a Moog relay to identify these faults, that is heating up of the rotor, okay, due to loss of excitation. Okay, so when offset is connected to a Moog relay, you can call that Moog relay as offset Moog relay. Okay, so this offset Moog relay is operated for AC currents and voltages at the generator terminals. So, and the relay this Moore relay is its setting is so arranged that the relay will operate whenever the excitation goes below a certain value and machine starts running asynchronously. Okay, so this offset Moore relay will operate whenever the excitation goes below a certain value. Okay, and a machine starts to run asynchronously during asynchronous operation. Why? Because during asynchronous operation, what will happen? The rotor gets heated up. Okay, so in this image you can see the Moore relay, offset Moore relay. This is our generator, this is our circuit breaker, this is the CT which is measuring the current in this line, and there is an this is the RX diagram. Okay, means this is the this gives the characteristics. This shows the characteristics of this offset Moore relay. Okay, this characteristic shows us that the impedance, whenever the impedance measured by this Moore relay, offset Moore relay, lies within this circle, okay, within this circle, then this relay will operate. Okay, so when the characteristics of this relay lie beyond this circle, this relay will not operate. You know, in Moore relay operation. Okay. So whenever loss of excitation is there, the relay characteristics will swing into this circle. Okay. So when the relay characteristic swings into this circle, then this relay will operate. So now under normal operating condition, when synchronous generator is connected to the grid, okay, under normal operating condition, when this synchronous generator is connected to the grid, it supplies lagging reactive power to the grid. Okay, this synchronous alternator will supply lagging reactive power to the grid system. Okay, and in addition to the active power, okay, it will supply active power as well as reactive power, and the power factor is lagging. Okay, and the impedance of the alternator is seen, if you see this RX diagram, it is seen in the first quadrant of RX diagram. Okay, so under normal operating condition, the characteristics will lie in the first quadrant. Okay, so during normal operating condition of the synchronous generator, the generator is supplying reactive power, lagging reactive power, and active power, and power factor is lagging. Okay, now if excitation failure occurs, okay, if the excitation failure occurs, then the synchronous alternator will start to work as an induction generator. Okay, this synchronous generator will start to operate as induction generator, and it will start drawing lagging reactive power from the grid. Instead of giving to the grid, it will start to take from the grid lagging reactive power. Of course, it will be supplying the active power to the grid. Okay, hence it will operate at leading power factor. So when it is operating as induction generator, due to loss of excitation, it will operate at leading power factor. Okay, so what will happen is the impedance characteristics of this induction generator will shift to the fourth quadrant, and when these characteristics swing into this Moore relay characteristics, the relay will operate. Okay, and the circuit breaker is open. Okay, so this is the loss of excitation protection of your alternator. Now let us see negative sequence protection of this alternator under unbalanced loads. Okay, under unbalanced loads, negative sequence protection. So if there is unbalanced three-phase stator winding is there, if the okay, so then if the three-phase stator winding currents are unbalanced, then it is observed that double frequency currents will be induced in the rotor. Okay, double frequency currents will be induced in the rotor. Consequently, the rotor will get heated up and it will get damaged. Okay, due to the unbalanced three-phase stator. Okay, double frequency currents are induced in the rotor, and hence rotor gets heated up and it gets damaged. Okay, so under unbalanced conditions of this three-phase stator winding, the phase currents have negative sequence components. Okay, the phase currents of the stator windings of the alternator or generator will have negative sequence components and rotating at synchronous speed in a direction opposite to the direction of the rotor of the generator. Okay, so under unbalanced condition, okay, the phase currents will have negative sequence components of this stator winding, and they will be rotating at, these currents will be rotating at synchronous speed in a direction opposite to the direction of the rotation of the rotor. Okay, therefore double frequency currents are induced in the rotor. Okay, so rotor overheating can also be due to unbalanced external faults which are not cleared quickly. Okay, if the unbalanced external faults occur in the rotor, due to the unbalanced external faults, the rotor may get overheated if that faults are not cleared quickly. Okay, so open circuiting a phase or a failure of one phase contacts of the circuit breaker can also lead to overheating of the rotor. Okay. Now, to save the rotor getting heated up under such conditions, we need a negative sequence relay. I hope you people remember we have already discussed about negative sequence relay. Okay, so this negative sequence relay will sense this and it will operate. Okay, so the negative sequence heating will follow a normal resistance law and hence will be proportional to the square of the current. Okay, so the negative sequence relay operation will be proportional to square of the current. You can see here. Okay, the heating time of this machine will be largely a function of cooling system employed. Okay, so how much time is taken for the rotor due to the unbalanced currents in the stator or due to the unbalancing of the external fault which is not cleared quickly, how much time is taken for the rotor to heat will depend on the functioning of the cooling system. Okay, so usually it is expressed in I square T equal to some constant K. So where T is proportional to, inversely proportional to the square of this current. So T is the time of operation of this negative sequence relay. I2 is the negative sequence component current and K is the constant proportional to the thermal capacity of the generator rotor. Okay, so minimum temperature, there will be some capacity for this rotor. So any equipment will have a minimum temperature resisting capacity. Okay, so if that minimum temperature resisting capacity exceeds beyond its range, then only it will affect the operation of that particular part of the machine or that machine itself. Okay, so this is about negative sequence protection of the electric generator under unbalanced load. Okay, so when this negative sequence relay senses the temperature of this rotor, okay, so it will if that temperature reaches the preset value, then this relay will operate and it will disconnect the unhealthy section from the healthy section. Means it will give signal to the circuit breaker and circuit breaker will open.